everyone. Welcome to our session. I'm Oli. I'm Solutions Architect at 47 Degrees, and I have a couple of podcasts about Scala, and we're co-presenting today with Andy, so welcome him too.
And hi, I'm Andy. I work on the Scala team at Stripe, where we're responsible for builds and infrastructure for our Scala repositories, mostly used for data and data processing. Do you want me to do the?
Yeah.
Yeah, so we have one mic, and I guess we're going to be talking over each other while the other person types. So we'll see how this goes.
Okay, we don't have any slides whatsoever, and we're really, let's finger out cross that everything will go fine, because we're going to use SCSI and rely on this fantastic internet here. And let's start a new snippet. So we're going to talk about recursion schemes. And Andy, let's start with your motivation. Why is it important?
So I like recursion schemes because they give us a really expressive way to build up or tear down data structures, and they allow you to really focus on your business logic. Yeah, so that's the main reason. It allows you to express really powerful algorithms with really, really simple steps, with a really simple encoding. It also lets you operate over many different kinds of data structures using the same code, which is something that we often like to do as functional programmers.
Yes, to give you a simple example, we wanted to talk about Skeuomorph, the open source library that we're building at 47 Degrees, but unfortunately I don't think we will have time today. But usually when you're working with some kind of protocol, for example, Protobuf or Avro, you're building your own data structure, and that data structure needs to be traversed at some point. You need to make some computation based on that, and recursion scheme is a technique which allows you to be focused on your business logic and avoid boilerplate almost completely. No internet, you're kidding me.
Internet's pretty important.
While we're trying to find a connection and connect to something, we can use Xfinity. We can talk about the most popular recursion schemes, data structure, which everyone uses at every project, I bet you. Any ideas? It's a list, guys. It's just a list. So what we're going to do a little bit of foreshadowing of what we're going to talk about today. We're going to grab two functions from standard Scala library. It's, oh, cool. We don't have slides, but we have cats, so our presentation is allegedly cute because of that. So we're going to talk about list, and the first thing that we want to do is just grab two signatures from Scala standard library, fold right and unfold. Okay, this is unfold. As you can see, this is just a standard. Are you fine? What can go wrong when you are doing live code independent on internet, right?
So many things.
Yeah, so many things. Your keyboard doesn't work.
The mouse isn't moving fast enough, and I can't see your screen. So.
Okay, let's start with it. And fold right. This is also a member of a list. So the first thing that we want to do with this is to clean up it a little bit. Meaning that we want to rename some type parameters, and also we want to pass a list inside of fold right because it's no longer a member of list, but we need to operate on something.
Screw that. Oh. You want it bigger?
Let's try that. Does it work? Yes, it's bigger. Okay, so let's pass list inside.
Nice. Great.
And let's rename it a little bit. We want to have an E type parameter because it stands for like element of a list. It will make more sense later on. Let's rename that for unfold 2. So we will have E and A. These functions are pretty similar, and this renaming will allow us to show that in more detail. So in order to implement that, the first thing that we can do, the only thing that we can really do, is pattern match on the initial parameter, because that's what would compile, right? If we have an empty list, we return the initial value. Otherwise, we need to call our operation and call recursively our same function with the tail and pass z and op. Right? Let's give an example and show how it works. So we will try to write a product function, and yes, this is just a multiplication of two integers. And then let's call this fold right with that function. So we pass an initial list, which is 1, 10, 20, with the initial value 1. Presumably that will return 200, because 1 multiplied 10 multiplied 20 is 200. Yeah, cool. Now, do you want to refactor this or implement unfold?
Let's go ahead and implement unfold.
OK, let's implement unfold. Again, using closer loop technique. The only thing that we can do here, we can call f with the initial parameter and then pattern match on the result. So in case we have no result from our computation, and knowing that we need to build some kind of list, we just return an empty list. In case we have an element, we just concatenate that with the recursion call. You were typing too fast. Recursion call of our function. So let's give an example again and make sure it works as expected. So what we want to build is the range function, which will generate a list of numbers going from 10 to 1 in this case. So we just got two integers. No, this is
that's right.
One integer. Yeah, we have a bit of a problem, yeah. Given one integer, we can return 2 values or no value at all. So that can be implemented pretty easy. Yeah, so let's see if it works. Range up. Ta-da! Okay, cool. So now, as you can see, in each of this function, fold right and unfold, we can do a little bit of cleanup so that we could get rid of passing z and op over and over again, or f in case of unfold again. So let's do that by moving the list parameter to the return part so that the function would return the function. Yes, in this case, we just use the kernel, and instead of fold right on tail and passing z and op, we can just call kernel on tail and remove this part. Yes. Yes, we need to change how we call our product operation, because now list is a last parameter. Right? But otherwise, it does essentially the same thing. Nothing has changed tremendously. Same 200, I guess.
Oops.
Yes. Okay.
Same thing to unfold.
And same thing for unfold. We pass the initial parameter into returning value and write a function, anonymous function, with the kernel again to get rid of passing this f around. Yes, and just instead of unfold, call kernel on a. Yes. This is the first step of our refactoring, and you already can see that unfold and fold right are kind of similar functions, but going further, we want to do more refactoring and change the signature of fold right.
Yeah, so what we're going to do here is fold right takes 2 parameters and unfold takes 1. It's possible for us to combine the 2 parameters of fold right to get 2 functions now that look much more similar. So first thing we can note is that we can produce this z value using, or excuse me, a b value using this z constant, or we can use our binary operator that takes an e and a b, a tuple eb, and produces a b. So you can think of z as a function from unit to b, and you can think of, well, the binary operator already is a function. You could also join those together and think of it as a single function that takes an either. So on the left-hand side, you're going to produce that initial z value. On the right-hand side, you're going to use the binary operator. Right. And so if you have an either with a unit on the left, you can more cleanly express that as an option of whatever was on the right. You can just discard that unit value. And what we wind up with here is the exact, or rather the dual of the function that we have from unfold. So instead of going to the option of the tuple, we are starting with the option of the tuple and going to a single result. So we're starting to make these 2 functions, fold right and unfold, look really similar, or much more structurally similar. Right? And to refactor, to use that single argument, just a simple replacement, and then making sure that we pass in none and some in the appropriate spots. Also, we have to refactor the product opt because now that also includes our initial value. It includes everything about our computation. Still the same fold right from before, computes the same result. It's a little bit less efficient. We're not really worried about efficiency right now. We're just trying to show that these are the same. Great. So that should work.
Yay.
Cool. Copy paste these before we refactor, like save fold right and save unfold. Cool. So what we want to do now is we want to really think about what these 2 functions are doing and kind of compare the 2 of them. And what we're ultimately going to do is we're going to take list, our data structure, and we're going to pull that out of our fold right and from our unfold. So we're going to abstract over our data structure and get a generic fold right, a generic fold, and a generic unfold. And to do that, we're going to look at the function first, our implementation rather, and we want to identify everything that is specific to our list, everything that's recursion related, and then really anything else. And we're going to identify 3 steps. The first step is we're unpacking or projecting our list. And you can see that because we pattern match on our initial list value. So we break apart our list. The second thing is that when we're at recursive points, which there's only one in our list, it's the tail, we're going to call ourselves. We're going to call kernel. And then the third and final bit is we actually do a computation, which in our example is computing a product. So we have these 3 steps. We break apart the list, we do recursion, and then we do our computation. And if we do that same analysis on unfold, we wind up with almost exactly the reverse. The first thing we do is we do our computation. That's going to produce this option of tuple result. We're going to inspect that and do some recursion when our computation says we need to do recursion, which corresponds to the tail of our list. And then finally, we're going to repack or embed back into a list. So we're going to smash things back into a list. So same 3 steps, almost the same 3 steps, but done in reverse order. And in one case, you're breaking something apart. In another case, you're bringing it back together. Cool. So what we want to do, and we don't have time to go through every step super slow, we're going to kind of make some jumps here for you. And if you want to go through this slowly, we plan on doing an unconference later, so you all should come to that, where we can just work through it real slow. Oli, wait, undo. No, save, fold. Oh, you already copy-pasted it? Yeah. Cool, all right. Whew. All right, cool. So what we're going to do is, it turns out that option of tuple, that carries all the information about our list through the computation. If you dive into recursion schemes, that's often called the pattern functor. But basically, we can use that to interface between our 3 different steps. So we can unpack our list into this option of tuple. We can do our recursion in the option of tuple, and then we can do our final computation using that option of tuple. It just kind of threads its way all the way through our code. And so what Oli's doing here is she's stepping out all 3 of those methods. We'll implement them quickly, and then we're going to take the apply method from our fold right and just call step 1, 2, and 3 in the correct order, and it's just going to work. Well, hopefully we get the types right, and then it works. Right, so if we implement these methods, then we just call step 1 first, we pass that to step 2, and then we call step 3. And this should compile. It's just going to throw an exception if we run it, so we need to implement these methods. Oh, we're removing step 3, because step 3 is simply calling our computation, so we're just going to call that directly. No need to have an additional function there. Great. This is the one time we actually want an error of that shape, so it worked. Let's go ahead and implement step 1 and step 2. For step 1, we need to unpack our list. So we're starting with that list. We're going to pattern match on it. There's not much we can do other than just stick the results in this option of tuple. Important to note that recursive point, the tail of our list, gets stuck in the second item, or the right side of our tuple, right? So that second element in our tuple corresponds to the tail of our list. The first item in our tuple corresponds to the first item in our list. So that option of tuple captures everything about our list. Right, so we pattern match, step 2, the perils of using SCAST. So for step 2, we're calling recursion only for the recursive point in our list. And so we've put that in the second item of our tuple. So if we get sum of a tuple, we're just going to call kernel for that second element in the tuple. So just calling the recursion only for the spots in our projection of our data where we need to. And if we do this correctly, it should compile. I think it compiled. It produced a result. So that worked, right? We just took, it's ugly, it's inefficient, but we just took fold right and we split apart what seems like a really simple implementation. We split it into 3 separate steps to isolate data from recursion from computation.
I'm tired of writing option, right?
So what we're going to do now is we're going to pull all this out, and before we do that, we're going to first introduce some type aliases. 1, because we need them, and 2, because it's pretty obnoxious to type option of tuple over and over again. So we're going to introduce type f of p, and that's going to be option of tuple with that right side kind of varying depending on what we're doing, because that's that recursive point in our list. And we're also introducing a type s. I think of this as structure, and this is our list of some element. And we're just going to replace all of these parts throughout our code. Uh-oh. Oh, you got to add the bracket. Yeah, forget. And the one at the end. Cool, that should work. Great, and we get the same result because it's the same code. So now what we can do, and I think we might switch here, but what we can do, we have a little bit more cleanup to do. Step 2, it's taking an f of s and going to an f of a b. If you're familiar with cats or just familiar with Scala in general, that looks a lot like a map on some kind of a structure, because it is. So we can, if we have a functor for our f, then we can just call map, right? We can call map and pass in kernel. So we can map over our structure and call kernel recursively at this, wherever it needs to be called. So we can replace step 2 with just a functor fmap. And we're going to use cats for that, which we've already added to the project. This part's not particularly clean just because we're using an option of a tuple, but we need a functor for an option of a tuple. So we're going to leverage some functionality in cats to build up a composed functor across those two structures. So we're asking for functor of option composed with tuple to give us a functor for the whole structure. Right? And so this should work. Step 2 can now be replaced with an fmap over kernel. And this should compile, it should get the same result. We have the same signature from before. We've just kind of fiddled with all the bits inside our implementation. Great. And step 2, we don't actually need it, a separate step. We can just call fmap directly in our implementation. Same thing. Great. So, yeah, we're going to switch. What we're going to do next is we want to pull out all of these types. And as we do that, we're going to wind up with a completely generalized fold that operates over any data structure. And Oli's going to walk me through that. So.
Okay, as you can see, the only thing that is tied to list type that is here is the step 1. We still do pattern matching on our data structure, and what we really want is to have a generic function which can be passed inside our fold right, so that for your specific data structure you could provide how you're going to project, how you're going to be unpacking it. Okay, let's pull S out first, probably, or let's do that in whatever order you want. Yeah, so list E in our signature of fold right doesn't make sense anymore. We're not tied to the list. So let's just say that it is some kind of structure that what S stands for. Then we can get rid of option as well, because this is, let's add functor instead of having it inside, yes. So, and we got rid of option as well, because this is a specific functor pattern for list. So now let's move project out of here. Project. Yes. We actually still need this implicit, right? We need this implicit for functor.
Well, we can recreate it in a second.
Okay. So maybe let's introduce the pattern functor type.
Yeah, so we
How about this?
Oh, we could type this whole thing out. We could type this whole thing out. We're just expanding our types, or we could introduce some more type aliases to make life a little easier.
Yeah.
Like I could expand S to list of E, I could expand the F to the option, but instead we're
Okay, so now we have a project list. So you could implement that for any recursive data structure and then just pass that inside fold right, and that would work just fine. So you could get rid of boilerplate, and you don't need to write this fold right yourself. You can use library like Droste or Matryoshka. What did you do?
I just moved the other other stuff away.
Okay.
We don't need it. So now we just need to pass project in.
Okay, let's pass project in and make sure that we still get the same result. Do we?
Yeah, gotta help Scala.
We're really running out of time. Okay, it works. So now, if we look at fold right, we can just say that it's no longer fold right. It's yes, it's cata, and our f is not f. Actually, we can give it name finally. Right, it's our algebra. And we could do the same refactoring for unfold.
We don't have time to go through the full
Yes.
refactoring for unfold, so if
you will have to believe us.
if you do, you wind up with the exact same result, just with the reverse ordering and the reverse computation for everything. So I'll go ahead and do that now, and then we can kind of just look at the two. But you get the same result, just the inverse.
Okay, so you just need your coalgebra, you need f as a functor again. Say that it's functor, yes. And the, it returns f of s. Then you need embed function, which goes from f of s to s. And then re-implement apply. Oh yeah, that's return s. Yeah, the first thing you do is coalgebra or our computation, then mapping over, and then embedding that into data structure. And this is anamorphism.
So earlier we took the project list and we pulled it out of our implementation and made it a little bit more generic. When we refactored to get Anna, we needed to do the same thing, and we would wind up with embed list, which also just looks like the dual of projecting. So we need to go ahead and do that now.
So you can see they're pretty similar. So we could think about like how to get rid of recursion in your data structure, and how to project or embed. How to have this option. In fact, contains two parts: how you break down your data structure. You have an element for your current step, and you have the rest detail for further steps. Same thing for your custom data structure. You need to have like parts, how you break down what you do on the next step of your recursion. So here we have cata and anamorphism, and yes, finally we've got all our pieces together, and now guess what we want to do, right?
Fuse them together. Do you want to talk through it or me?
No, I don't know. We don't really have time. We need to do that. So basically,
we definitely have time. Let's do, so if you think about computing the range and then computing the product over all the results of that range, you wind up with factorial. So let's fuse these together, and you get a hylomorphism. So we unfold, we don't actually save it to a list, and then we immediately fold it back down. And so if you look at the signatures for Anna and Cata, they look exactly the same because they wind up being exactly the same. So we can refactor a little bit, rename it, and we can come up with a really clean and fun factorial implementation.
I want to put emphasis again on the fact that Hyla allows you not to save memory by not creating a list as an intermediate step. You just go exactly from values, from unfolding it to folding it without creating an intermediate step. Which doesn't necessarily mean that recursion schemes is the most performance way to build your application, but woohoo! We also could have built like quick sort, for example, using Hyla as well. Why are you looking at me like that? We're not going to do that right now, but that's possible. So factorial of 4 is 24.
Cool. I think that's mostly it, but we'd love to show more recursion scheme stuff if you want to come to an unconference later. You can do more advanced stuff like fusing more of these algebras and coalgebras together to do multiple computations in one pass and other really fun stuff. But that was it.
Yeah, I also wanted to mention that initially I wanted to talk about Skeuomorph, the library. So if you're going to unconference, please join us. I will show how to use another data structure and apply anamorphism and catamorphism and how to actually use that in practice and how we use that in production. All right.
Great. Can we give them a round of applause? And thank you guys very much. That's really tough to do, that live coding.